Thank you for joining us for this month's webinar, where we'll be talking about our Apex 60 head and looking at some of the considerations involved when you're thinking about getting into 5-axis cutting. We'll take a look at the design of the mechanism, we'll do some programming, and then we'll do a little bit of 5-axis cutting. So hopefully after this, you'll have a better grasp of what's entailed with 5-axis WARDJet cutting, and we'll answer some questions at the end as we're going along. If you have any questions, please feel free to type those in. If we're not able to get to your question during the webinar, then we'll follow up with you afterwards. So enjoy and see you here in a bit.
First, we'll take a look at the design of the Apex 60 5-axis head. So the Apex 60 is here on the left, and then on the right we have our older version 5-axis head, which was called the InfiniWinder. A couple changes between the InfiniWinder and the Apex 60. First of all, the Apex 60 is designed as an integrated unit here. The Z carriage and the 5-axis device are all built in together, whereas the InfiniWinder here on the right, the Z carriage was separate from the InfiniWinder. So by having the Apex 60 now as an integrated device, to reduce the costs, or able to basically sell the Apex 60 about half the cost of what we used to sell the InfiniWinder at. InfiniWinder was a bit bigger. Apex 60 had much more compact design. Also, the Apex 60 is better designed for handling taper angle control. On the InfiniWinder head here on the right, we were grabbing the cutting head up here. So when it came to doing taper angle control, where you have to make fairly quick motions going around a corner and such, with the C-axis up here, you basically have to swing this whole device around when you're coming to a corner, so it's not as conducive for doing things like taper angle control. The Apex 60 head, we're grabbing the head closer to the tool tip. With the motors mounted the way they are, it reacts much more quickly, and it's a much more accurate device by grabbing the cutting head closer to the tool tip. So as we spin this around, the C-axis motor, which is this one up here, which spins it if you're looking down, spins it in the C-axis, mounted at a 10-degree angle. So that helps to save space, and also allows us that when we're doing small angles, don't have to rotate the C-axis as much, so very quick reactions in that way. The A goes up to 60 degrees, so that's why it's the Apex 60. Found that most customers primarily need 5-axis for doing 45-degree bevel cuts, and few customers need to go beyond 60 degrees. Being able to go 60 degrees, if you have two 45-degree edges that intersect, your maximum angle is basically a little bit over 57 degrees, so this allows us to cut 45-degree bevels on parts. The InfiniWinder could go up to 90 degrees, which gave it more flexibility, but really there were a few customers that needed to go to that sort of angle. And then this also has the height setter built into it. So we'll see here in the programming how that works. You can basically have this touch off to find the top of your material, and then bring the cutting head down to its appropriate cutting height. So with that, let's take a look at programming. There are several things that are going to go into creating the most accurate 5-axis part possible. First of all, we have to look at the flatness of the table. So we do everything we can to ship the machine with grates that are as flat as possible in that table, so that when you put your material on there, you've at least got a nice flat surface for that. Obviously, if you've got grates in there which are not perfectly flat, if I exaggerate this a bit, you've got grates in there and you've got a 1/4 inch difference or something from front to back or side to side, or a combination of both. No matter how flat your material is, you put that super flat material onto grates which aren't perfectly flat, then your bevel cuts are going to be off, because the cutting head's going to be assuming that the material's in one location, but it's going to be changing as it's cutting along there. Conversely, we've got if we do have our grates in there nice and flat, but you've got material which has a bow in it, again a bit exaggerated, But 5-axis head again is assuming that the material is flat and in the position where it's going to be. But if you have material like this, you're going to have a different intersection of the stream with the material here than if you're cutting here. So it's very important to have flat cutting surface as well as a flat workpiece. And then the final piece of the puzzle is also having a 5-axis mechanism, which is calibrated, which later here we'll show you a little video on how the calibration of the Apex 60 works. There are a couple things that we have to talk about in particular with the Apex 60 head when it comes to the programming. And first thing is rewinds. We've got a couple limits, C-axis limits that we have to be aware of. So we're looking down on the C-axis of the Apex 60. If the cutting head is pointing off at the 9 o'clock position, this is considered 0 degrees. And if it's pointing straight out this way towards the front of the tank, that's positive 90. If we're pointing to the right side of the tank, then that's either positive or negative 180. And if it's pointing straight towards the back of the tank, then that is negative 90 or positive 270. Maximum C positive value is 270, and the minimum C value is right around here, negative 223. So to avoid hitting either of those limits, you have to pay attention to the location of your lead-in and the type of cut, bevel cut that you're doing, whether it's a top bevel, bottom bevel, inside cut, outside cut. If we're looking at a part from the side and we're looking to do a countersink on a hole, so we'll generally do the vertical cut first, and then we'll come back and do the countersink. If we're looking down on this hole, and this is going to be our countersink. If I were to put my lead-in point over on the 3 o'clock position of this hole, we would be starting over here and our stream would be projecting in this direction, and that would correspond with a C angle of 0. And if I'm going counterclockwise around this hole, we're going to go through 0, 90, 180, and then we're going to hit this 270, and I'll have to do a rewind. I'll stop cutting, head will spin around, come down, pierce again, and then continue around to get back to 0. Most people want to avoid that, especially for abrasive cutting. You'll have a bit of a blemish there where it re-pierced. Water only might not be a big deal. If we were to go the other direction around the hole, starting in that location, we'd start at 0, we'd go through negative 90, negative 180, and then we hit the negative 223. Then again, it would want to do a rewind to continue on from there. So for an top bevel like this on inside 3 o'clock would not be a good position to start at. If we start over here at the 9 o'clock position, however, now we're pointing this way, which corresponds with starting at either positive or negative 180. Usually it's going to pick negative 180. And again, if we're going counterclockwise, it's going to start at the negative 180, go through negative 90, go through 0, positive 90, and then be able to get back to 180 without hitting either of those limits. So generally for top bevels, inside cuts, you want to start your lead in at around the 9 o'clock position. Similar fashion if you're doing a bevel cut around the outside, top bevel cut around the outside. So we're doing a bevel cut something like this around the outside of the part. If I start somewhere along this right side of the part for that cut, again we would be starting at what corresponds with either the positive or negative 180, and as it makes its way around there, we shouldn't hit either of those limits. Now if we want to do a bottom bevel, then it's just the opposite. So for bottom bevel on an inside cut, we do want to have our lead-in placed at around the 3 o'clock position, because that will give us our start angle pointing like this. And then if it's an outside bevel cut, we would want to have our lead in somewhere on the left side of the part so that it's pointing in this direction when it starts the cut, which would correspond with that 180 position. This is a chart that summarizes that. If you're doing a inside bevel on the top of the part, you'll want to start on the left edge or the 9 o'clock position here. If you're doing inside bevel cut bottom bevel, then you'll want to start over here on the right side at the 3 o'clock position, and then opposite for the outside. If you're doing outside cut top bevel, you want to start over here at the 3 o'clock position, and then if you're doing a bottom bevel on the outside, then start at the 9 o'clock position. Now the other thing to talk about is singularity. So singularities can happen when the axis of motors are in perfect alignment, and then you tell it to go to the next position, and it can go either one of two ways, and it might go the right way or it might pick the wrong way to get to that point. It's talked a lot often with robots, and sometimes depending on the configuration of 5-axis WARDJet devices can also have singularities. So the Apex 60 head, if we are between -90 and -223 and the cutting head A angle passes through 10 degrees, then we have a singularity area, and when it hits that, it could tilt the head one way or the other to get to the next angle. So to avoid that, oftentimes you can just rotate the parts. I've got an example here of a part. So we're coming out of this steep angle here where we're going over to 54 degrees or so, and then it's straightening it up as it comes to this edge here. And you can see here we go from 10 degrees, past 10 degrees, and potential here for singularity and having the cutting head spin around in the wrong direction when it hits that point there. And yes, oftentimes you can just rotate the parts to get it to the point where it doesn't hit that singularity. So if I take this part and I rotate it, I think 90 degrees around Z, and then we take a look at it again, then now when it comes out of that point there, we're passing by the 10 degrees, but because the C is 0, it's not within the -90 to -223, we don't have a singularity and shouldn't have any issue with that. So that's the other thing to keep an eye on. It comes more into play when you're doing more complex parts like this, where the bevel angle is tilting, changing as it's going around the other part. And it's also why we always do tilted piercing. If you do vertical piercing, your A angle is of course 0, and depending where your lead in is, as it tilts over to get to whatever angle, then it could pass through that singularity point and spin around. So we always recommend doing tilted piercing with the Apex 60. Let's go ahead and program some bevel cuts in WARDCAM. We'll put a couple bevel cuts on this part here, top right hand corner, hit my next button. Got my Apex 65-axis machine HS for height setter and 1440 nozzle orifice combination. Choose our material and our thickness and hit our next button. Top left corner, hit our auto button for our vertical cuts, and then over here we've got our bevels tool. If we want to put top bevel on a cut, turn on the whole contour button here and just left click where we want to put the lead. So this will be a top bevel inside cut. We want this at the 9 o'clock position. If we also want to do a bottom bevel on that same cut, over here switch to bottom, and then we'll want to put that lead in position over here on the right side, 3 o'clock position. And then we hit our next button and we can click on the CNC button. And we've got this code here, which tells the height setter to come down, do the initial height set to establish the proper standoff distance, and then depending on how flat your material is, you can set a stamping radius, and when it gets beyond that distance from where it did its last height setter, then it'll do another height setter. So in this case here, we scroll to the bottom, we see that we've got 5 times that it's doing the height setter in this program. and shows us that since the last height setter, in this case it was only 2.3 inches versus our height stamping distance is set to 6, so here it just uses programmable Z to come up and down, versus on this cut here it had been 7.2 inches since the last height setter, and it does the M402 code to activate the height setter. Depending on the flatness of the material, if you want to change that stamping radius, the options menu, edit variables, on the height sensors tab, scroll down and we have the stamping radius, which right now I've got mine set to 6, so if this was flat material I could set that maybe to 12 or something larger, and then rather than doing 5 height setters, we'll see here now it'll only do 1 for the initial. You can also drop points to make the height setter probe at certain positions for particular geometries. If we wanted our stamping radius at 12, but maybe for the outside cut we did want it to do a height setter, but it's not outside of that 12-inch radius since the last height setter, what we can do is, back in the first step in the process, we can basically draw a point where we'll be doing where we want our height setter to be for the outside cuts. And on this parts tab here, under point functions, we have an option for height setter. So we got the green line, just click there, that puts it into the cut sequence. And then like before, we would do our cuts for our bevel cuts and such. I'll just put these back on here. And then we just need to move this down to right before the outside cut. So before the outside cut, it'll do the height setter and then do that outside cut. So if we make our CNC file again, and scroll down to the bottom, we'll see now that we've got 2 height setters, and it's going to wrap it to that point that we drew, do a height setter, and then move over slightly and pierce and cut the outside. Now the other capability that we've talked about briefly is taper angle control. Of course, one of the key things about WARDJet cutting is that you'll get taper. The faster you go, the more taper that you're going to get. If you want to reduce that taper with the Apex 60, over here on the right we have the taper tool, so we can turn on taper angle control. And if we look into the material database, we've got this taper tab, and grayed out there we've got our anticipated amount of taper, and so WARDCAM will adjust for that accordingly. If you find that you're still getting more taper than you want, you can use these fields here to further hone in those taper numbers. If I go ahead and make my CNC file now, I'm going to start getting rewinds, because those taper angle control cuts are 5-axis cuts, and we have to look at the positioning of those leads for those in order to avoid those unwinds. So if we go back to the toolpath area, basically what we'll want to do is move these lead positions such that, again, we're pointing towards that negative 180 position. In this case here, if you can imagine looking at this from the side, so before, when we were doing a countersink, of course we were doing something like this. Now we're looking at doing taper angle control. So we're basically tilting in the opposite direction. Essentially it's like we're doing a bottom bevel, because we're tilting the head in slightly this way to reduce taper. So when you're positioning your leads for taper angle control, you basically want to think about it like we're positioning our leads for a bottom bevel cut, which we're doing. which means for inside cuts, we're going to want our leads to be at the 3 o'clock position, and then our outside lead, we're going to want that basically around the 9 o'clock position. Since I'm going to be moving my lead in for the outside, I'll just go back to the first step of the process here, and I'll just delete that point and put it down here where I'll put my lead in for the right side or left side of the outside cut. And then we'll go back in and add the height setter function to that. We'll do our auto button and then move our lead positions. And we'll put our bevel cuts back on here. Move this back down to where it needs to be. Hit our next button. And now we've got it, our part's got the taper angle controls in there, so we have the A angles in there to adjust for the taper. And now let's look at programming a more complex bevel cut in our IGEMS package. So we're going to go ahead and show video cutting the 6 pieces that go into making this box here. This has some various bevel cuts, can help with welding. It's got a countersink on there, we've got some tab and slot. So some pretty involved 5-axis cuts here that we'll see in the video, and I'll take one of these parts and program it so you can get an idea how that's done here in our IGEMS package. So IGEMS is an optional package that has more capabilities than WARDCAM, especially when it comes to doing more complex bevel cuts like are in a part like this. We'll go ahead and step through that process here. I'll go through and program this part here. In our 5-axis module here, open up that file. Depending on where it was drawn in space, right now the grid represents basically the top of our table. So you use this Z height button here and basically move this so it's laying on the table. And you can set your 0 point, which is that black and white circle, set that somewhere on the corner of the part if you're just doing a single part. So you box option here and set that lower left hand corner top of the part, and then I can go through and pick curves that we're going to use then to add toolpaths to. So the curves basically dictate the projection of the stream. I can pick surfaces and it'll find whatever edges it can find there. Also on something like this where we've got the X bevel cut here, you got that intersection of the 2 edges, click on pick edges, and then you can individually select edges if you need to. And for the outside cut, we're going to do a little bit of a different edge than what's already selected. This will be our top edge, which we've already got on that one there. For the bottom edge, we're going to need to select this and that and do the same thing on the other end here. In this case here, I'll click on pick edges and choose that and this and that and that one there, and then I can just do my N for next and follow it the rest of the way around here. And we want to go that way and that way, and that should give us the edge that we need so we can do that portion of the outside cut. And we can go ahead and add toolpaths. So this screen here for the slots, I can just click on the auto button, and wherever I left click is where it'll put the lead in point there. If I want to do taper angle control on any of these cuts, I can select that for cuts individually. And we'll do the bottom bevel. Click on the plus button to add a new cut. This is going to be our top edge, starting here and finishing there. And this will be our lower curve. And we got our lead in and lead out. And with an open contour cut, you just want to make sure that you've got your toolpath on the correct side of the part based on the direction that we're going there. Our curve is set to the right, offsetting to the right, which is good. Offsets into the scrap of the part. And then click on the plus button again. This will be our upper curve this time, starting here, finishing there, going in this direction, and then this is our lower curve. And can do our lead in and lead out. Now in this cut, because of the way the curves are drawn, we've got these red lines here indicating that we're going beyond 60 degrees. Got a couple ways of fixing that. Cut type right now is set to ruled. I can click on here and I can add additional connection points to basically specify the angle that I want to go to avoid going beyond the 60 degrees. I can click on this plus button here and I can choose a point maybe here and somewhere down here, and we'll see if that's enough. So we can click on done and simulate again, and looks like we stay below our 60 degrees there. The other way to do that, if we just delete that and close out of here, is rather than doing it as ruled, we have the variable choice, which gives you more options, and we can click on edit to edit this, and again we can add additional points in here, and you can do things like tilting the head manually if you need to, if you've got cut that you need to do that. So there's a lot of different options that you can do with the variable command here. So I'll just add a few connection points along here, and if you double click on it, you can then do things like choose point and straighten that up a little bit. So a couple different ways of adjusting things like that. And then for the outside cuts, do our plus button again and select that other curve that I'd selected here, and start here and end here, and we're so for the outside cut, we'll do the plus button again. Upper curve will be here, starting here, finishing here, going in this direction, and then this is our lower curve, and put the lead in and lead out on there. And these all have the taper angle control added on there. So you can add taper angle control also to bevel cuts. We can adjust rapid heights between cuts. Click on this button here. If you decide you only need to lift a small amount between cuts, can just click on that button there and adjust your rapid heights. If you're using the height setter, you can also specify the height setter to go off at certain cuts, and that's done in the toolpath area. So if on this cut here we want to make sure that it did a height setter on that cut, attribute box, choose HS, and it'll do a height setter before that pierce. Click on the process button, we can do a simulation, check to see if we have any singularities or unwinds. So we've got two height setters. We've also got singularities going on. Basically in this cut here we got one, and then a couple others going on there. So oftentimes that can be fixed simply by rotating the part. So we'll go through and we'll go ahead and just I'll rotate it 180 degrees and see if that does it. So now no rewinds, no singularities. We do the height setter at the initial pierce point like we would always expect to do, and then further down in the program on that cut that I had specified to do the height setter, we'll have one there, which is right here. And then with respect to taper angle control, the numbers for the taper angle control in IGEMS are in your material database. And in this case we're looking at 1/4" aluminum. Scroll down a bit here and plug in values top and bottom for the rough quality and the extra fine quality, and then it determines what the angle is there that it has to adjust for. The other thing that you can do in IGEMS is this VOC, variable offset control, where there's a slight difference in the kerf width of your stream when you're cutting slow versus fast, and IGEMS can adjust for that with the VOC numbers that are in here. So with that, let's go ahead and watch it cut. this video we'll walk through how to do the calibration on the Apex 60 head. If you're an Apex 60 customer and like this video in regular speed, we'll send that to you. First thing we do here is cut a fixture somewhere on the table that will be able to place our calibration tool. And this is the calibration tool. And next thing we'll do is take off the high pressure lines from the cutting head, the abrasive inlet, the actuator, and then this will allow us to swing the Apex 60 head around to all the various angles that we need to do for the calibration process. And then eventually here we'll also put in the tooling ball that's used to on the dial indicator. And the first thing we do, once we've got that fixture in position, is we want to square up, make sure the A and C axes are square. And this process here, we're just using the move panel and dial indicator to check first the C axis to see that it's square. Basically move back and forth and plug in the numbers and bump the C axis accordingly until you get that with where it's within less than a thou variance when you make the little move there from this. And we'll do a similar process on the A-axis arm. There's also calculation you can do where if you know what the difference is, you can just use math to calculate how much you need to rotate the A-axis arm to square it up, which we're showing here. So that'll reduce the number of times that you have to go back and forth. And once you've got the A and the C axis squared up, then you put the calibration fixture into the fixture that we cut, and we just want to make sure that the that surface there on the dial indicator is nice and square. And once it's squared, then we've got a 6-step process that we go through, move the Apex 60 6 different positions, and basically type in the variance that we see on the indicator as we're going around here. And those numbers are put into a formula that calculates what we need to do to calibrate that head. So important when you're doing this to step through all 6 steps of the process. You don't want to do maybe 3 and then just jump ahead. Just want to step through that entire process, and then you can step through it again just to verify without changing any numbers that the indicator stays basically at 0 or pretty close to it. And then you are good to go. So that's a quick rundown of the Apex 60 calibration process. And if you are an Apex 60 customer and would like that video, we can send you that link so you can watch it at real speed.
There's our welded up box. Hope you enjoyed watching that, and hopefully you've learned something about 5-axis water jet cutting today. Let's go ahead and see what sort of questions we got.